Hi all and welcome to a new video of the Data Structures and Algorithms course. Today we will talk about binary trees. Before we continue, please take just a second to like the video as it helps with the YouTube algorithm so that more people can benefit from this course. Also, please subscribe so that you will receive notifications when a new section of our course will be released. Now let's move on with understanding binary trees. A tree is a frequently used data structure to simulate a hierarchical tree structure. Each node of the tree will have a root value and a list of references to other nodes, which are called child nodes. A binary tree is one of the most typical tree structure. As the name suggests, a binary tree is a tree data structure in which each node has at most two children, which are referred to as the left child and the right child. There are a few variations of binary trees. We will look at the three most popular ones, and those are a full tree, which is a tree in which every node has either 0 or 2 children. The perfect binary tree, which is a binary tree in which all interior nodes have 2 children and all leaves have the same depth. And a complete tree, which is a binary tree in which every level except possibly the last is full and all nodes in the last level are as far left as possible. For binary trees, we have a concept called traversing a tree. And there are three ways to traverse a tree. The pre-order traversal is to visit the root first, then traverse the left subtree, and finally traverse the right subtree. The in-order traversal, which is to traverse the left subtree first, then visit the root, finally traverse the right subtree. Typically, for binary search tree, we can retrieve all the data in sorted order using the in-order traversal. And the post-order traversal is to traverse the left subtree first, then traverse the right subtree, and finally visit the root. Deletion process will be in post-order. That is to say, when you delete a node, you will delete its left child and its right child before you delete the node itself. All the traversals can be done in both recursive or iterative manner, and we will see that in the coding section of the video. The time complexity. In average, and you will understand why I say in average in the drawing explanation of binary trees, access, search, insert, and remove are done in O of log n time complexity. For the usage of binary trees are used to represent a non-linear data structure. There are various forms of binary trees. Binary trees play a vital role in software applications. One of the most important applications of the binary tree is the searching algorithm. Now that we understand a bit, at least in definition, what binary trees are, and we looked a bit over the variations, how to traverse, and the time complexity of binary trees, let's move on to the drawing explanation part of the video, in which we will draw a binary tree. I will also explain common terminologies when it comes to binary trees, and then we will move on to the coding section, where we will traverse a tree in pre-order, in-order, and post-order, both iterative and recursive, and both in Java and in Python. Welcome to the drawing explanation of the binary tree. As you can see here, I have drawn a binary tree, and a tree is nothing but a variation of a graph. We will talk about graphs later in our course, but now let's just focus on the binary tree. Let's start by explaining a bit what a binary tree is. As we saw in the keynote, a binary tree is a tree structure in which each node has at most two children, which are referred to as the left child and the right child. So let's see some common terms related to binary trees. The node at the top of the tree, it's also called a root node, and this is a node that has no parents. Then 20 here would be the left child, 60 would be the right child. The root is connected to the left child and the right child with a branch. We call this a branch. Also, you will hear the term leaf when it comes to binary trees or to trees in general. A leaf is a node which has no left child nor right child. So in this case 10, 30, 50 and 70 are all leaves. So these are some common terms related to binary tree that we have to remember. Now, one other thing to know about trees is that we always have the branches coming from top to bottom. We cannot have node 70 pointing back to node 60. That would be just a regular graph. We also cannot have more than one branch towards a node, meaning that node 30 cannot point to node 50. That would again be a graph, because we would have 60 pointing to 50 and 30 pointing to 50. This is also not possible because this is not a tree. Also, we cannot have disconnected trees like this. This is again not a tree. These are two trees or a disconnected graph. As we saw in the keynote, there are three ways to traverse a tree: either pre-order traversal or in-order traversal or post-order traversal. Let's take each one of them and understand them a bit. So let's talk about the pre-order traversal. Pre-order traversal is to visit the root first, then the left subtree, and finally we will traverse the right subtree. So in this case, pre-order would look like first the root node 40, then we move to the left subtree, and here we go to 20, then we go again to the left subtree and we go to 10. There is nothing left at 10. We go back up, root has been visited, then we go to the right subtree and we have 30. Once again, 30 doesn't have a left child or a right child. It goes up to 20. 20 has been visited. We go back to 40. 40 has been visited. Then we start traversing the right subtree. And here we have 60. At the left of 60 we have 50. Nothing at the left or right of 50. Then we go back up. 60 has been visited. We go back down to 70. And now all the nodes have been visited. So this is the pre-order traversal. Now let's have a look at the in-order traversal. Let's write it right here at the bottom. For the in-order traversal, we first traverse the left subtree, then visit the root, then finally we traverse the right subtree, right? So in this case, we would go down to the leftmost node, and that is 10. 10 doesn't have any left or right, so we're gonna print 10. Now the parent of 10 is 20, so I'm gonna go to 20, and then right is 30, so I'm gonna print 30. All three nodes have been visited. Then we go back up the root, so we have left visited, root is 40, and then we go to the right, but to the right we go to the leftmost node in the right subtree, and that is 50. Once again we visit the root, 60, and then 70 on the right side. So it's left, root, right. Also for the subtrees is the same, left, root, right. And as you can see, the in-order traversal prints the values of the nodes in a sorted order. And now the last traversal is the post-order traversal. For the post-order traversal, we traverse the left subtree first, then we traverse the right subtree, and finally we visit the root. So in this case, the leftmost value is 10, so this will be the first value that we print. Then we go back to the root. We don't print the root yet, we go to the right. Then we print 30. Left and right leaves have been visited. Then we go to 20. Then we go to visit the right subtree, and in the right subtree we go to the leftmost value, which is 50, then to the rightmost value, which is 70, and then we go to the root of the subtree, which is 60, and then at the end we print 40. And this is the post-order traversal. Now, traversing a tree, it takes, of course, O of n, because we have to visit all the nodes in the tree, where n is the number of nodes in the tree. Now, for all other operations like access, search, insert, and remove, we say in average it's done in O of log n time. And as we know, O of log n is much better than O of n. And why are they done in O of log n in average? As we see here, the tree we have, it's a perfectly balanced tree. All subtrees are also balanced, meaning that we have the same number of nodes to the left of the root as we have to the right of the root. We can also have a less perfectly balanced tree, where let's say we only have this type of tree, but it's still good because the left subtree has the same level as the right subtree. And in this case, where the tree is very well balanced, everything is done in O of log n, because if we need to find a value or we need to remove a value, we would either visit the left subtree or the right subtree. There in the left subtree or in the right subtree, we would also go only to the left or to the right. So we see we keep dividing by 2, and that's why it would be done in O of log n time. Now, if we have a completely unbalanced tree looking something like this, which is also a binary tree but is completely unbalanced because the depth of the left subtree is much higher than the depth of the right subtree, which in this case is 0. And this brings me to another point. What is the depth of a tree? Is the distance from the root to the leaf of the tree. So in this case, the left subtree depth is 2, the right subtree depth is also 2. In this unbalanced binary tree version, the depth of the left subtree is 1, 2, 3, and the depth of the right subtree is 0. So in this case, access, search, insert, and remove would be done in O of n in worst case scenario, because if we want to access the last node, we would have to go through all the nodes of the tree. But we say that in average, and in an interview, it's important for you to mention the difference between a balanced and a completely unbalanced tree. That's why we say that in average, the operations are done in O of log n time. And the last topic I want to discuss is the variations of a binary tree. So let's make some room here, and we have the first variation is the complete tree. Now, a complete tree is a binary tree in which every level except possibly the last is full, and all nodes in the last level are as far left as possible. Meaning what? If we have a tree like this, like we saw before, this is a complete tree. Why? Because every level is full, including the last level. Now, we also have a complete tree, even if the last level is not full. Meaning that if we remove this node here, this is still a complete tree, because even though the last level is not completely full, it is filled from left to right. If I will remove this node here, this is not a complete tree anymore, because my tree is not filled from left to right. We have here one node that is not filled. So this is not a complete tree. Also, this is a complete tree because we are again filling the tree from left to right on the last level, which doesn't have necessarily to be full. The next type of tree I want to talk about is the full tree. Full tree is a tree in which every node has either 0 or 2 children, meaning that we take again the example we had above. This is a full tree. Why? Because each node has 2 children, minus the leaves which have none. Now, this is not a full tree anymore, because we said that a full tree is a tree in which each node has either 0 or 2 children in case of a binary tree. In case of a k-ary tree, every node has to have either 0 or k children. But now we're talking about a binary tree. So in this case, we either have 0 or 2 children. That's why the example here, now it's not anymore a full tree. But if I remove this node, this is a full tree. Why? Because every node has either 2 or 0 children. And the last type that I want to talk about is a perfect binary tree. And a perfect binary tree is a tree in which all leaves have the same depth, meaning that, once again, if I take the example above, this is a perfect binary tree. Why? Because all leaves have the same depth. If I add a node here, this is not a perfect binary tree, because our leaves, they don't have the same depth. So now we kind of understood how binary trees look like. We understood also the different variation of binary trees. We understood how to traverse binary trees and how much time it takes to traverse. We also learned why having a balanced binary tree is actually important for the time complexity when we need to access, search, insert, or remove. Now let's move on to the coding part of the video. We will begin with the Java implementation of the tree traversal, and for that we first need to create a tree node class that I'm gonna define here, and I'm just gonna copy paste it as I already have it implemented. And as we can see, a tree node has a value, a reference to the left child and a reference to the right child, and we will also create a constructor in which we will initialize the value of the tree node. Now let's begin traversing a tree. Let's define the class, and we will start with the pre-order traversal and the iterative version of the pre-order traversal, which will take a tree node as parameter, and that tree node will be the root of the tree. And we will say if root is null, then we return. We will define a stack, and you will see that for all the iterative traversals we will define a stack, and I think it makes sense if you think about the fact that we can also do it recursive. And if you remember from recursion, the foundational data structure of recursion is a stack, so we will define a stack here which will hold three nodes. Let's also import array list, list and stack because we will need them later. And now I'm gonna push the root node into the stack. As we saw, the pre-order traversal first tackles the root node and then the left subtree and the right subtree. And while our stack is not empty, I'm gonna define a tree node current, and it will be the last value in the stack. I'm gonna say stack.pop, and I'm gonna print it. Or if I want to return a list instead of void, I'm gonna add it to the resulting list. But for this example, let's just print it, and I'm gonna print current.var. Now we will go and check if the current.write is not null, and if it isn't, I'm gonna push in the stack current.write, and I'm gonna do the same for the left node. And what I suggest is, once you write this method, just try to manually debug it using a stack. That will help you understand better also how the recursive function works. And basically this is it for the pre-order iterative method. Now let's go ahead and test this method. Now here in the main class of my REPL, I will first create a method which will basically create my binary tree. I'm gonna copy paste it. Now we're ready to test. Let's get a tree traversal, and now we can call the pre-order iterative method. Also let's define the tree. Find this traversal, and this should be good. And as we can see, we have the root first. As we said, the root node is 40, then the left side 20, 10 and 30, then the right side 60, 50 and 70. Now let's do the exact same traversal, meaning the pre-order traversal, but recursively. So I'm gonna say public void pre-order recursive, and I'm gonna take in a tree node root, and I'm gonna say if root is null, then return. This is the base case, and now you'll see how simple it is. So I'm gonna print first the root, then I'm gonna call my method pre-order recursive for the left side of the tree, and call it again for the right side of the tree, and basically this is it. And you see how simple this is compared to the iterative one. Let's also call it and see that we get the exact same value. So in our class main here, I'm just gonna call the traversal.preorder recursive of the binary tree. Let's run it, and as you can see, we get the exact same values. Let's continue with the in order traversal. We start again with the iterative version, then we go forward with the recursive version. So I'm gonna define a method here, public void in order iterative. I'm gonna take again the root node as parameter, and the same thing. If root is null, then I return. Otherwise, once again, I'm gonna define a stack, and in this case I'm not gonna add the root to the stack. I'm just gonna define a current node which will be equal to root. And now the while is a bit more complex, so I'm gonna say while stack is not empty, or my current node is not null, then while current is not null, I'm gonna push current into the stack, and I'm gonna go to the left subtree. So current will be current left. Now once I'm done with the left subtree, I'm gonna say current equals stack.pop, because as we saw, the in order traversal is left root right. I'm gonna print it, and then I'm gonna go to the right side. And basically this is it. Let's also test this method. So here I will do traversal, and I'm gonna call the in order iterative traversal. Let's see how this looks. Yeah, and as you can see here, the in order traversal return the sorted order of the nodes of the tree. Let's also do this recursively, and once again you'll see how much more simple it is. So I'm just gonna copy paste the pre-order recursive, and I'll show you how easy it is. So instead of pre-order, I'm gonna call this method in order recursive, and let's remember to call it also here. And the only thing that is different is that I'm gonna go through the left side first, and then I'm gonna visit the root, and then I'm gonna visit the right side, and basically this is it. Let's also call this method and see how it looks like. Traversal dot in order recursive of our binary tree. Let's run it, and indeed, as we can see, it's the same result as the iterative version, only that it took so much less to develop. And now let's go on with the last traversal, which is the post order, and we're gonna go again with the iterative first. And in this case I'm gonna return a list of integer, because if we don't do this, the implementation will be a bit more complex if we just want to print in the method. But because I want to show you a very easy implementation of the post order iterative, we will return this time a list. So post order iterative, and once again we pass the root as parameter. Let's initialize our list. This is values, new array list, and of course I'm gonna return values at the end. And now if root is null, I'm gonna return the empty list of values. Great. So now once again we do the exact same thing. We define a stack. Just like the pre-order, we're gonna push the root in the stack, and we're gonna say while not stack is empty. Basically it's the same way as we implemented the pre-order, only with a small trick, and I'm gonna show it to you now. I'm gonna say tree node current is stack.pop, and if you remember there, we printed the value, or we added it to a list in case we wanted to work with a list, and we'll do the same here, only that instead of adding it at the end of the list, I'm gonna add it always at position 0. So basically it will put the nodes in the correct order, and that's why I wanted to use a list, so that we don't have to remember 3 ways of traversing a binary tree. We just have to remember 2, and we know that the post order is the same as the pre-order, only that we had always in the beginning of the list. And then it's just the exact same. If current left is not null, then stack push current left, and we're gonna do the same for the right side, and this is it. Then we will return the values. Let's test the method, and as you can see here, because we return a list, I streamed it, and for each value I'm gonna print, and basically that's the only difference between this and the previous two. And I'm gonna run it. Yeah, and you can see we have the orders in post order. Let's do the exact same for the recursive way, and once again I'm gonna copy the in order, I'm gonna call it post order, and the only thing I'm gonna do, I'm gonna put the root at the end, and that's it. This is how simple the recursive way is. And now let's test this method again, and we're gonna call post order recursive of our binary tree. Let's run it, and as you can see, it returns the exact same values as the iterative version. So this is it for the Java implementation. We saw how to traverse a tree in both recursive and iterative ways for all three: pre-order, in-order, and post-order. Now we will do the same in Python. Now for the Python implementation, let's start by also creating a tree node class. So here I just import list from typing. We will need it a bit later. And I defined a tree node class which has a value, a left child, and a right child. And now let's define our tree traversal class. And we will start with the pre-order iterative traversal. So I'm gonna call my method pre-order iterative, and what I will pass, it's the root node of the tree, which is of type tree node. I'm not gonna return anything here, and I'm gonna say if root is none, then return. I'm gonna define a stack, and I'm gonna append root to the stack. Now while my stack is not empty, I'm gonna define a current node which will be stack.pop, and I'm gonna print it current.val. and I'm gonna define an end here as well, just because I want them to be printed on the same line. And I'm gonna say if current write is not null, or we can just say if current write, then I'm gonna append current write to the stack, and I'm gonna do the same for the left side. If current left, then stack append current left. And this is it. Let's test it. So what I will do is I will create a main method here, and in this main method I'm gonna define the nodes. And of course you can see for node with value 10 I have nothing for the left and right. For the root node I'm gonna have node 2860 for the left and right, and then I will call the pre-order iterative, and let's see what it will return. Before we do that, let's also call the main method. So I'm gonna say if name is main, then call the main method. Now we can run it, and we see we obtained the pre-order traversal. Let's do the same for the recursive pre-order traversal. So I'm gonna define here a pre-order recursive, which will take again self and root, and will return nothing. And I'm gonna say again, if root is none, then return. Otherwise, I'm gonna print the root value, and I'm gonna call my method for the left side, pre-order recursive for root left, and the same for the right side, pre-order recursive root.right. Let's call this method and see what it will return. In my main method here, I'm gonna call it, and as you can see it returns the exact same as the iterative version. Now let's go on and implement the in order iterative method. So I'm gonna define an in order iterative. It will take in a root of type 3 node, and I'm gonna return none. Same thing, if root is none, then I'm gonna exit the function. Otherwise, again, we define a stack and the current node which takes the root value. And I'm gonna say while stack is not empty or current is not none, then while current is not none, I'm gonna append current to the stack, and I'm gonna move on to traverse the left subtree. So I'm gonna say current equals current left. Once I'm done with the left subtree, I will update current with the stack.pop, and I will print the value of current. Then I'm gonna go ahead and traverse the right side of the tree. And this is it for the in order iterative. Let's also call this method in the main method and see what the result is. Oh, here we have to copy some method. Let's run it again, and we see we get the sorted order of the values in the tree, which is what the in order traversal does. Let's go ahead and implement the recursive version, and for this I'm just gonna copy the pre-order recursive so that you can see how much more simple the recursive version is. And here I'm gonna call this in order recursive, and for the in order we said that first we go through the left subtree, then we visit the root, and then we visit the right subtree. So all we have to do here is go to the left, print, go to the right, and this is it basically. Let's also test this method and see that it returns the exact same as the iterative one, and we see it returns the exact same. Let's move on with the last traversal, which is the post order traversal, and again we start with the iterative version. I'll just show you a trick here so that you don't need to remember also how to do this. You just need to remember the pre-order traversal, and here we'll do the same, only with a small trick. That's why in this case I'm not gonna return none, I'm gonna return a list. So I'm gonna say post order iterative self and root, which is of type 3 node, and in this case I'm gonna return a list of int. And what I will do, I will just declare values as list of int, and I'm gonna say if not root, then I'm gonna return values. Once again we define a stack, we add a root to the stack, and while stack is not empty, current equals stack.pop. So until now it's just the same as the pre-order. The only difference is that in values, instead of appending at the end, I'm gonna insert current value always at position 0, and that will arrange my elements in the right order. And this is it. For the rest is exactly the same. I'm gonna say if current left is not none, then stack append current left. If current right, then stack append current right. And let's not forget to return values. So let's test this method. we call it here in our main method. So if I'm gonna run it, once again, stack the pop is a method. Let's run it, and we see we get the post-order traversal. Now let's do the same with the recursive version, and once again I'm gonna copy paste the in-order recursive. I'm just gonna call it post order, and the only thing that changes is that before we visit the root, we visit the right side, and that's it. This is how simple it is to do it recursively. Let's call this function in the main method and see that it returns the exact same as the iterative version. Let's run. We receive the exact same. I really hope that you found this video informative and you enjoyed this section about binary trees from our algorithms and data structure course. If you did, or if you have any suggestions, please take a moment to leave a comment below. Don't forget to like the video, as it helps with the YouTube algorithm so that more people can benefit from this course. Also, please don't forget to subscribe and press the bell button to receive notifications when the next chapter of the course will be released. Thank you for watching, and I'll see you in the next one.